Hello and welcome to the Unit 10 podcast on section 16.2. Today we're going to be talking about heat and chemical reactions and processes. I'm Mr. Sakaguchi,
And I am Mr. Lin.
and let's get started. So, one way to measure heat is through something known as a calorimeter. This is basically a device that is used for measuring the amount of heat absorbed or released during a chemical or physical change.
So the components of a calorimeter are pretty straightforward, but you have an insulating cup, you've got some water inside that cup, and a thermometer inside. And the entire point of this equipment is to contain the amount of energy so that only the water is absorbing energy. So when you have a chemical reaction occur or a physical change occur, and energy is released or absorbed, however much energy is being, let's say, released by a substance gets absorbed by the water. And since we know how much water there is and the specific heat of water and how much the water changes temperature by, we'll know exactly how much energy was being released by the chemical reaction. And if we figure that out, we know how much heat is being produced.
And this occurs at constant pressure, because if pressure wasn't constant, we'd have another factor that we'd have to deal with.
Right.
So calorimeters can be as simple as two styrofoam cups with a cork in a setup such as this, or it can be a very fancy setup. But the idea here is that the heat gained by the water is going to be equal to the heat lost by the object, and as heat flows, and we know the temperature, we can calculate using the specific heat equation to calculate how much energy the water absorbed, which we can attribute to our object.
Right.
So here's an example of using calorimetry data to determine specific heat for another substance. So let's suppose we have 125 grams of water in our calorimeter, and the initial temperature of the water is 25.6 degrees Celsius. Then what we do is we take a 50-gram piece of metal, we heat it to 115 degrees Celsius, and then we put it into the water. And if the final temperature of the water metal sample is 29.3, what is the specific heat for the unknown metal?
So here we've got all sorts of numbers jumbled all over the place, but it's best to categorize what is, or categorize all the labels. So here we can take a look at, from the equation here, we're taking a look at the amount of heat from the water, and is going to be the amount of heat lost from the metal. So heat gained from water is from the metal. So the heat gained by the water is going to be shown by the specific heat of water, which is going to be 4.184, that's a constant. Then the mass of the water that we know of is 125 grams. And then the change in water temperature. A lot of students have difficulty identifying this part. We know that the water started at 25.6, and then the final temperature of the water metal sample is 29.3 degrees Celsius. So it's the difference between those two. So when we put all of these factors into the equation, we come out with 1900 joules. Now that's 1900 joules of energy that the water absorbed. If the water absorbed this much, that means that piece of metal that cooled down released this amount of energy.
So now that we know how much energy the metal released, we can solve for this specific heat of the metal, because we have our Q, which is the 1900. It's negative because this was lost. We have the mass of the metal, which was 50 grams, and then we have the change in temperature of the metal. Now remember, we're talking about the metal, not the water. So the final temperature was 29.3, and the initial temperature of the metal is 115. So the negatives actually cancel out through this process, and we end up with 0.44 joules per gram per degree Celsius.
Right.
And then we could use this and in conjunction with a specific heat table to maybe identify the metal.
Right.
These are just some ideas behind energy and how it kind of fits into how we measure heat flow. Because if you don't, you have to basically determine where the heat is emanating from and going to. And if you can't define that, it makes these chemistry problems with energy hard to follow. So these are a series of terms that helps us kind of together track where the energy is flowing. So thermochemistry is just basically studying the energy component in chemistry. The system is where we're focusing interest in terms of where energy is going. The surroundings or anything outside of the system. The universe is the system and the surroundings.
Right. And then, since we're dealing with thermochemistry, enthalpy is a new term for you, and that's how much energy is contained within the system at a constant pressure. Because if you adjust the pressure or change the pressure, that alters our calculations. And there's also the enthalpy of the reaction, delta H reaction. That's how much energy is changed in the substance before and after the reaction. So final minus initial, or products minus the reactants. Whenever you have a chemical reaction that winds up absorbing or causing the system to gain energy, that's an endothermic reaction, and these have positive values. Endothermic reactions tend to feel cold in the hand because it's absorbing energy or heat from your hand for the reaction to occur. Then you have exothermic reactions, which have a negative energy sign because they are releasing energy. The system is losing energy to its surroundings. So in your hand, an exothermic reaction will feel warm because energy is leaving the system and it's going into your hand. And then, so here we have our change in enthalpy at a constant pressure will result in the overall energy change.
That's right. That's it.